Hello. Previously, we have covered the complete response of second-order circuits. Today, we will conduct some second-order circuit exercises such that you can solidify your understanding of these concepts and also learn how to apply them. Alright, in this first exercise, we need to find the initial conditions I0, V0, the first derivative of I, the first derivative of V at t is equal to 0, and the final values of I and V at t is equal to infinity. And we have a circuit where a 12-volt source is connected to these two branches before t is equal to 0. And at t is equal to 0, the voltage source is disconnected from the rest of the circuit. Let me start solving this circuit by creating the equivalent circuit for t is less than or equal to 0. We will have plus minus 12 volts. Then we will have a 6 ohm resistor here, but the inductor will behave at steady state as a short circuit, so I don't draw the inductor. Then I will have here 4 ohms. And the capacitor will behave as an open circuit. So in other words, here I will have plus minus V. If I define this point as the reference node, and assuming that there is no voltage drop over this 4 ohm resistor, here I will have V as well, and my current I is flowing this way. Simply here at t is equal to 0, V0 will be equal to 12 volts because we have the voltage source directly connected to this V node, and I0 will be equal to 12 volts divided by 6 ohms, since the current flowing through this side will be equal to 0. It will be equal to 2 amperes. So basically I found my initial conditions for the circuit, I0 plus and V0 plus, as V0 is equal to 12 volts and I0 is equal to 2 amperes. You might ask, here we have the plus signs. Why doesn't these values change when the switch is opened? Because these are integral based variables. In other words, the current over an inductor cannot change instantaneously. The voltage over a capacitor cannot change instantaneously as well. Therefore, I0 minus, I0 and I0 plus will be equal to each other. As the second step, I want to find the derivatives of I and V just at the time when the switch opens at t is equal to 0 plus. I will draw my equivalent circuit. 6 ohms, 2 henries, current I passing through this element. Here I have 4 ohms and my capacitor, plus minus V. And I can use this current I to write my KVL, and accordingly I will have 6I plus 2 di over dt plus minus V plus 4I is equal to 0. Now at t is equal to 0 plus, I can write that this will be 6 times I 0 plus 2 times di 0 plus over dt minus V 0 plus 4 times I 0 plus again. This is V0 plus I 0 plus is equal to 0. So this will be equal to 10 times I0. I0 is 2 amperes. 10 times 2 plus 2 times di 0 plus over dt plus minus, in this case, minus V0. V0 is 12. Minus 12 is equal to 0. And from here, when I solve this, I calculate di 0 plus over dt as 12 minus 20 over 2 minus 4 amperes per second. So I found this initial condition as well. Alright, now we need to find dV0 plus over dt. For that, I will define this current as I capacitance, and I capacitance is equal to minus I, and this is equal to C times dV over dt. And at t is equal to 0, we will have I capacitance is equal to minus 2, which is equal to 0.4 times dV0 plus over dt. And accordingly, dV0 plus over dt is equal to 5 volt per second. Here I should have a minus sign. Now I found the initial derivative of the voltage as well at t is equal to 0. So what will happen when t goes to infinity? When t goes to infinity, this circuit does not have a source which supplies energy. It has only passive elements which can either store the energy, the inductor and the capacitor, or resistors which can dissipate energy. Eventually, this circuit will most probably oscillate with voltage and current, and finally the I infinity will converge to 0 amperes and voltage infinity will converge to 0 volts, because this is a stable circuit without a driving input. Alright, the natural response of a second order circuit is given by this differential equation, and obviously this is the complete response of this circuit, because we don't have an input to the circuit, so this right hand side is equal to 0. We are being provided with two initial conditions. V0 is equal to 20 volts and dV0 over dt is equal to 0 volts, and we need to find Vt. The first thing I will do in order to solve this question is to write the characteristic equation, which will be s squared plus 2s plus 1 is equal to 0. And now I will solve this. S12 is equal to minus 2 plus minus square root of 4 minus 4 over 2. And I have two overlapping roots at minus 1. Accordingly, the system will have a critically damped response. And this critically damped response will have a form Vnt is equal to A plus Bt times e to the, since the pole is at minus 1, minus 1t minus t. And now my problem is that how to find A and B, so I will use the initial conditions for that. Vn0 is equal to A times e to the 0, which is 1, which is equal to, from this initial condition, 20 volts. So I found A easily. Let's find B using the first derivative of V at t is equal to 0. dVn over dt is equal to minus A plus Bt times e to the minus t, and plus, it's a mistake, plus b times e to the minus t. If I evaluate this expression at t is equal to 0, I end up with minus a plus b is equal to 0. Since I know a is equal to 20, I can write b is equal to A and 20 volts as well. And accordingly, my natural response for this circuit becomes 20 plus 20t times e to the minus t, and I conclude the solution of my problem. We need to find the value of resistance R such that the natural response is critically damped. When I look at this circuit, I see that the circuit can be reduced to a series RLC branch if I were to be able to reduce this to a single equivalent resistance. And that R equivalent is simply 60 ohms in parallel with R, which is equal to 1 over 1 over 60 plus 1 over R, and this is equal to 60R divided by 60 plus R. Accordingly, I can draw my circuit as R equivalent 0.01 Farad capacitance, 4 Henry inductor, and I can just kind of like close this part such that I can write the KVL around this loop. Alright, I will define the voltage over this capacitance as V and write my KVL. R equivalent times I plus V plus 4 times di over dt will be equal to 0. Another equation I can write is the constituent relationship of the capacitor, which is I is equal to 0.01 times dV over dt. And if I plug this into this equation, I end up with 0.01 R equivalent times dV over dt plus V plus 0.04 times d squared V over dt squared is equal to 0. And if I were to multiply this by 25, I end up with d squared V over dt squared plus R equivalent divided by 4 times dV over dt plus V is equal to 0. Now, in order to find the critical damped response, I need to first write the characteristic equation, which is S squared plus R equivalent divided by 4 times S plus, this is not V, this will be 25. V's plus 25 is equal to 0. From here, I calculate S12 as minus 0.25 times R equivalent, everything divided by 2, then here plus and minus square root of R equivalent divided by 4 squared minus 4AC, so it's the minus 100. For critical damped response, I need to have this determinant part equal to 0, so accordingly I have R equivalent divided by 4 squared is equal to 100. From here I get R equivalent is equal to 40 ohms, and I have this equal to, from this relationship, 60 R divided by 60 plus R, according to 2400 plus 40 R is equal to 60 R, and R becomes equal to 120 ohms. In other words, in order to have critical damped response, here the R value should be equal to 120 ohms, and the equivalent resistance here should have the value of 40 ohms. For the ideal op-amp circuit, find the differential equation for I of t. Now you have two options. One, you might panic. Second, you might tell that I know how to solve op-amp circuits. I know how to write differential equations for circuits which contain RLC elements. I will solve this. I recommend you choose option 2. Alright, my non-inverting input is connected to the reference node, so here I will have 0 volts, and accordingly I will have 0 volts here at the inverting input as well. The current which flow through the resistor will not be able to flow to the input terminals of op-amp, and it will directly flow this way. Let me define this point as V out, and I can simply write V out is equal to L di over dt. This is good because the question asks me to find I of t. And secondly, I can write this equation. Vs over R will be equal to C times D. The voltage will be 0 minus V0 over dt. Accordingly, I can write this as Vs over R is equal to minus C times dV0 over dt. And wherever I see V0, I can plug in this expression, and then this becomes minus C times L times d squared I over d t squared is equal to Vs over R. if I were to write this with the di squared over dt squared is on the left side by itself, I end up with Vs over minus Vs over RLC on the right side. So the equation for the I is governed by this differential equation. Obtain Vt for t greater than 0, and we have a 20 volt input to the circuit when t is greater than 0. Wait a minute, this is a trick. This input is not 20 volts after t is greater than 0. When this is t and this is the input voltage, our voltage is 20 when t is less than 0, and it decreases to 0 and it becomes 0 afterward. So let us draw our equivalent circuit for t is less than or equal to 0. So what will that be? Here I will have plus minus 20 volts. Then here I have my 5 ohm resistor. The capacitor will behave like an open circuit, plus minus V. And this inductor will behave like a short circuit. Assuming that here I have the reference node, the voltage at this node will be equal to V. And therefore I will have V0 is equal to 20 volts. And no current can flow through here, and all currents will flow through 5 ohms. So therefore I0 over the inductor will be equal to 0 amperes. So this way I found my initial conditions for this circuit. Now let's draw this circuit for t greater than 0. Obviously the voltage source will disappear and I will replace with a short circuit. Then I will put here my 5 ohms. Then here is the capacitance 1 over 16 farads. And we have lastly our inductor, not a resistor, inductor here, 1 over 4 henries. But since I have here the short circuited part, then this 5 ohm resistor will not pass any current because all the currents will be going through the short circuit and it will be effectively bypassed. So therefore I can remove this. And I end up with my final equivalent circuit. Here I have plus minus V, and here I have I flowing through this. And this circuit has only 2 elements in series with each other. Actually, in order to find the differential equation for this circuit, I could have used the differential equation for the series RLC case and equate R to 0, but I have a terrible memory, so I will use KVL in order to find the differential equation. I have the I going through the inductor and indeed the capacitor, and I can therefore write simply V plus 1 over 4 times di over dt is equal to 0 as my first equation. And secondly, I can write I is equal to C dV over dt. C is 1 over 16 times dV over dt for the second equation. And I can plug in this equation into that one, and I will end up having V plus 1 over 64 times d squared V over dt squared as my equation. And accordingly, the characteristic equation will be s squared plus 64 is equal to 0, and the roots of this system will be s1, s2 is equal to plus minus j8. So in other words, it is 2 roots which are imaginary and they are complex conjugates. So since the roots will not have real part, negative real part would mean exponential decay. Positive real part would mean exponential increase. So there won't be any decrease or increase, but oscillations. Let's figure out what will be the exact equation for this circuit. So I will use a modified version of the equation for the underdamped case. Accordingly, my natural response V and T will be equal to A1 times cosine AT plus A2 times sine 8t. I am omitting the term e to the minus real part of the roots, because this will be, since the real part is equal to 0, this will be equal to 1. And in order to find the a1 and a2, I evaluate my function at 0, where this whole expression becomes a1, because sine 0 is 0, and a1 is 20. And in order to find the second a2, I will do another trick. Now let's take the first derivative of the natural response. dvn over dt is equal to minus 8 a1 times cosine, not cosine, sine 8t plus 8 times a2 times cosine 8t. And at t is equal to 0, this expression will be equal to 8a2. And I have one more equation. We had found I is equal to 1 over 16 times dv over dt. And from here I have dv0 over dt is equal to 16 times I0, and this is equal to 0. So in other words, this expression will be equal to 0, and from here I get A2 as 0. Finally, my final expression for the circuit becomes A1, which is 20 times cosine 8t. This is my final solution.